We're going to try to model a solution, and then we're going to predict solubility using a table. So I handed out that table. Once we get to that, if you need one, I can hand one to you. And then we're going to talk about predicting which solvent will dissolve. We'll do some of these topics just in ALEKS. It's just easier to look at them in ALEKS. And then we're also going to look at the effect of temperature and pressure on solubility, especially for gases, because I think we're not as familiar with that. Okay, where is the... All right, so when we are modeling a solution, what you're going to do in ALEKS is it will have some pictures, it will have a compound, and then you just pick which picture matches what the solution will look like. So these are some questions that you need to check. Is the compound that you're modeling that is soluble, is it molecular or ionic? And then are there polyatomic ions? And this is going to help you decide what this compound will look like when it's dissolved in a solution. So the first part of this is if it's molecular, then molecular compounds will break up into individual molecules. The chemical bonds are very strong and do not break when the compound dissolves. So here are some examples. What do we look for when we're looking for something that is molecular? What kind of elements are in a molecular compound? So what is our criteria for having a molecular compound? We have molecular and we have ionic. What types of elements? All nonmetals. Good. So both. Okay. We could also say just no metals. So if we look at something and it has no metals, then it's going to be molecular. Then those chemical bonds are going to stick together. So the carbon is not going to break apart from the hydrogen. The carbon is not going to break apart from the chlorine. They're all going to stick together. They're going to stick together as a molecule. So this is like if I imagine what sugar looks like when I add sugar, I'm going to have all these sugar molecules floating around, but the sugar molecules themselves are not going to break into pieces. Okay, the next is an ionic compound. So ionic compounds, what are we looking for? So molecular, we're all nonmetals. What about ionic? What do we see in ionic? Good. Ionic compounds have a metal and a non-metal. Okay, or a metal and a polyatomic ion. Okay. So these ionic compounds are going to break into their ions. So if we have an ion, we're going to have, or if we have an ionic compound, we're going to have a positive charge, a cation, and a negative charge, an anion. So when we put an ionic compound into a solution, it breaks into those ions. The polyatomic ions are like molecules. The polyatomic ions don't break apart at their bonds. So if you look at the polyatomic ion list, most of the polyatomic ions have only nonmetals. So they have covalent bonds that are going to stay together in solution. So let's look at, we have some examples down here. So let's look at this first one. We're going to do that one later actually. Let's look at this one. So what ions do we have that form sodium hydroxide here? I need to turn on my actually. Okay. What ions do we have here? This is ionic. Which ones? OH what? What's the charge? Do you remember? Negative one. Negative one. Good. So we have this charge. And what's this thing? What charge does Na have? Positive one. Good. Okay. Oops. Positive. Okay, so we have this thing floating around in solution, and we have this thing floating around in solution. They're not gonna. This is not gonna break apart. This has a covalent bond, so this will stay connected, but the sodium is gonna break off from the hydroxide. Okay, so that's what's happening in an ionic compound. If we have something like, so this is kind of a weird exception. This is ammonium chloride. We have no metals, but we have a polyatomic ion and an ion. So here we have this ion, ammonium, and that has a positive charge. So this will be floating around in the solution, and chlorine will be floating around in the solution. So the hydrogens don't break off of the nitrogen because this is a covalent bond. But because the chlorine and the ammonium are ionically bonded, they are going to split apart in solution. So the Alex topic is going to give you a compound, and then you have to identify the correct picture. So this picture would have something with 5 atoms bonded together and something separate with another ion floating around. Does that make sense? Okay. All right, and then there's one exception to this, and we will talk more about this in chapter 9, because chapter 9 is all about acids and bases. But this comes up occasionally. For some reason, they put a few acids in chapter 8. So we're just gonna briefly go over this. So watch out for acids in this chapter. I'm going to give you this list. You will have to memorize this for chapter 9. But for chapter 8, you just need to identify if it has a hydrogen that can act like an ionic compound. I guess. Okay. So acids are an exception, because if we look at our list of acids, we're not going to really talk about bases. But if we look at acids, these are strong acids. They all have a hydrogen at the beginning. So look at all these. This hydrogen at the beginning acts like an ionic compound, and the hydrogen becomes an H+ ion, and then we get this polyatomic ion. So this one's called nitric acid. We have this proton that breaks off, and we have this hydrogen, positive hydrogen, and this nitrate polyatomic ion. Okay. So what you're going to look for is there a hydrogen at the beginning of the formula? That's going to tell you that it's probably an acid, and that's going to break apart in solution. So if I modeled this in solution, I would have a hydrogen ion, or that's also called a proton, and we'd have this nitrate ion, which I think the Lewis structure is like this. So again, this part of the compound, this part of the acid is not going to break apart. This is a covalent bond, but we're going to have this part over here and something like this floating around. And I need one hydrogen for every nitrate. Great, it's a charge element. Okay. So this doesn't happen very often, but it happens enough, and it occasionally happened on the test last year. So you need to know that if there's a proton at the beginning, it's going to act like an ionic compound. That's what acids do. And then we'll spend all of chapter 9 talking about acids and bases. Okay, question about that. I don't know why they added that to, I think we probably should tell them that they need to fix that. Watch out for that. All right, questions, thoughts so far? We're doing all right for fifth period? We'll spend all of chapter 9 on acid bases. So we'll come back to that. Okay, so we need to go ahead and draw. So, and Alex, you picked a picture, but I don't have pictures, so we're going to draw what happens. So if we have SF2 in solution, is this molecular or ionic? This is molecular. So we need to, in our model, we need to represent this as a molecule. So I'm going to draw the Lewis structure. We have something like this. Okay. So I need to look for something in my picture where I have 3 atoms bonded together. And then to have a solution, this would be my solute. To have a solution, I also need the solvent. So I think most of the time our solvent is going to be water. So in my model, I would also show my solvent. I might want to show another one of my solute molecules. Okay, but basically I just need to look for something that this should be a molecule. All of these should be attached together. Does that make sense? Okay, let's try a different one. How about this one? What kind of compound is this? This is ionic. What ions are made from this compound? What do we get out? Okay, and what charge does Fe have? 3+, good. And then what's the charge on chlorine? We've already seen it once. Good. And this, we need to make sure that the ratio is correct. This is telling me I have 3 chlorines for 1 iron. That's the charge balance. So every time I draw 1 iron, I need to draw 3 chlorines. Okay, and so these will be separate. And then I also have my solvent, so I'm just going to draw a few waters. Okay, and Alex, you don't have to draw it, but it will have you find the correct picture. Okay, does that make sense? So we're looking for an ion, and then 3 ions to charge balance the other ions. Okay. All right, how about this one? This last one. What? Ionic, good, thanks. So what ions are made from this? K. And what charge is on K? Good. And then what's the charge on, so if this is plus, what must be the charge on NO3? Negative. Okay, and this is a polyatomic ion. So NO3. So this is going to be something like this, where we have 4 atoms bonded together with a charge. So in my picture, I'm going to look for something like this. And then if I have another potassium, I better have another nitrate. I didn't draw the minus. Somewhere in my picture so that they charge balance. I can't have the incorrect number of charges. And then I also have water floating around my solvent. Or whatever the solvent is. Okay, does that make sense? So you're just going to identify the correct picture. Make sure the picture has the correct number of ions. Make sure if it's ionic, the correct thing split apart. Make sure if there's a polyatomic ion, the polyatomic ion bonds are not breaking. Okay, all right, let's keep going. Oh, I think you guys have that. Okay, did I miss anyone with this paper? You have this paper. Does everyone have this? Okay, so it's also an Alex. So okay, if you don't write on this, you can use this on the test. So otherwise, you can use the Alex. I copied this from the Alex data, which you also get on the test. That's why I feel okay about giving it to you on the test. So we're gonna practice some. Let me pull up my Alex. We're gonna practice an Alex topic with this solution. All right, so look over this table. What is this table using? Has anyone used it yet? No, no one's used it yet. Okay, so what is it telling us? When you're looking at this table, what do you see? Let me pull that up here. So this is color coded. That's important. So this is for the topic. It's called predicting solubility, predicting precipitation. So this is like our lab. We did, I think in lab 6, you mixed, I think like 9 different things together. You mixed like 3 and 3, and you did a table, and you saw what became cloudy or became a solid. This is just like that, okay? So somebody did an experiment for all of these different ions. So anions are at the top, cations are at the bottom. This is kind of like the topic where in I think chapter 3, we made like this kind of table. Do you remember this table? And we had to like, this makes a compound with this makes a compound with this. Do you remember that? Okay, this is kind of like that, but it's just a giant table. And it's telling us if it's soluble or insoluble. So green means it's soluble. What does that mean?
It dissolves.
It dissolves, good. And red or yellow means that you're gonna get a solid. It's gonna be cloudy. So this question that we're gonna do is asking us, is something going to be solid? So we're looking for no or slight. If it's no or slight on this table, then we're gonna click yes. Because it's a precipitate. Yes, it precipitates, and it's no or slight. This is telling me no, it's not soluble. It precipitates. Yes says it's soluble, it dissolves. I won't see a solid. Okay.
What is precipitate?
Precipitate means just like crashes, like falls out. Yep, becomes a solid. Yep. Or means insoluble. Okay. So we are going to do one of these together, and then we'll see how we're feeling. So generally, I don't think that I've ever seen this happen, but so generally these are going to be soluble. You're going to mix, just like in our lab. Soluble thing. So clear solution plus clear solution, you're going to see if it forms a precipitate. We're predicting. So what we have to do is we have to, this is soluble, and we're adding it to this is soluble. We're going to check if we switch the metal with the anion, if that precipitates. So I need to check, I don't need to check magnesium bromide. I need to check manganese and sulfate. And I need to check nickel and bromide. Does that make sense? And then if it is a no, if it's insoluble, if it precipitates, then I need to put yes, and I need to write the formula. Okay, so go ahead. So let's look at, we're looking for manganese and sulfate. So look on, so manganese is Mn. So look on your table, look at Mn, manganese, 2, and sulfate. So along the top, look for sulfate, and then match them up. So is it soluble or insoluble? Manganese sulfate. Manganese and sulfate? I'm getting that it's soluble, yes. Okay, let's pull this up. Come back here. Okay. So manganese is Mn. That's kind of a tricky one. Sulfate is over here. So yeah, be careful. Sulfide and sulfate are tricky. Manganese and magnesium are tricky. So just make sure you're looking at the right one. So this is all just looking at the table type of question. So this says soluble. Okay, so let's check the other one. Do you remember what the other one was? I don't remember. The other one is nickel bromide. So nickel is here, bromide is here. So that is soluble. So what should we put? Is there a precipitate? Wait. So everything is soluble, so we're going to put no. If it's yes, if everything is green, we put no. If we have red or yellow, we're going to put yes. That's confusing. Okay. All right, so the next one we're going to check is sodium. So again, these ones are going to be soluble. We're looking to see if the cation switching with the anion is insoluble, just like in our lab. So is sodium plus nitrate soluble or insoluble? Sodium plus nitrate. Do you see soluble yes or insoluble no on the table? Soluble? Okay, I also see green, soluble. Okay, so that one's good. How about the other one? Ammonium chloride. So look there. Ammonium is NH4 plus ammonium chloride. Oh my gosh. Also soluble. So we're going to put no precipitate. So that's okay. Okay, last one we're looking for iron and hydroxide. So this is iron 2 and hydroxide. Or potassium and sulfate. So iron 2, hydroxide is a no. So that means it's going to precipitate. So that means we're going to put, yes, something is a solid, something. So then we have to write the correct formula. And so we need to do this charge balance. So we have Fe2 plus, and we have OH minus, and we can get those charges from the table. So then we're going to do the crisscross. This is from chapter 3. So our formula would be FeOH2. Okay, does that sound familiar? So this part should be like familiar. We should have seen this before. Probably oops. I'm a little bit confused about ammonium chloride because isn't that what we made in the tube? All right, but if we dissolve it, okay. Okay, do you want to try another one, or do you think that you can do that on the Alex test and homework?
Can you do another one?
Yes, we only got to practice one. More practice. Okay, so which compounds should we check here? So remember, they're going to change. So we're going to look at iron, the metal, and then the sulfide. So iron and sulfide. So you're saying no, iron and sulfide is a no. Okay, so that means it's a solid. So we can just go from there. So that is yes. So if we get a no or a slight, don't put yes. It's kind of backwards. Okay, so what is the formula for iron sulfide? Iron 2 sulfide. So look at the charges. So if you're stuck, just look at the charges. So right out, we have iron 2, and then what's the charge on sulfide? The -2, and that's on your chart, so you can just look. And we crisscross. So if you're stuck, just show your work. And then we have iron, 2 irons for 2 sulfurs. We can't leave it like this. It's ionic, so we need to simplify. So we're going to divide by 2. So now, oops, that's a really weird F. So that's our formula. Okay, question. Are we doing okay? Giving me some funny looks. Okay. I've never seen them give you more than one that precipitates, and I've also never seen the solution A or solution B be a precipitate. So hopefully that's true. Okay, the next one. What should we look at to see if it precipitates? Good, potassium and nitrate. So that's soluble. And then what about ammonium and hydroxide? Yes. Okay. So these both precipitate, or yeah, these soluble. These are both soluble, so the answer is no. Yes.
How do you know what to look at to like find out which one?
So we're going to do. We're going to switch potassium and nitrate. So this is soluble, and this is soluble. They're both clear solutions, and we're going to add them together. And so the only way they can precipitate is if they trade. The metal goes with the anion, and the cation goes with the anion. So we have 2 pieces, and they're just switching their 2 pieces. So this is like 1, and this is 2, and this is like 1, and this is 2. So this one is going to go with this 2, and this one is going to go with this 2.
Yeah. And
that's what we're checking.
Okay.
So we're looking on our table with potassium and nitrate, and ammonium and hydroxide.
So do they both have to be like?
Just one of them has to be a no or slight. Yeah. Okay, so tell me, Stockton, for this one, which ones would we check?
Potassium chloride.
Yep.
Hydroxide.
Good. Yep. Okay. So look at that last one. Is there anything that will be a precipitate? Will anything be insoluble or a no or a slight? Okay, good. And then, so that's going to be yes, it precipitates, something precipitates, and we decided that it's going to be zinc hydroxide, excuse me, and what's zinc? What's the formula? So zinc is 2+, what's the charge on OH?
So ZnOH2.
Good, and make sure you put those parentheses because you need 2 hydroxides, good. Good. Okay, how are we feeling? Or do you think you could do that, practice it in Alex, or do you want to do another one? I guess we should check, make sure that we're doing it right. Okay. You okay? Okay, all right. Okay, so we're gonna go back to our notes and then we'll come back to this Alex and do some more topics together. Oh. Okay, we did this in Alex already, so we're good. Okay, so this is a little bit long. There's a question that is another reasoning question. So you could write this or you can just kind of reason through it. So the main thing is like dissolves like. Okay, so ionic compounds will dissolve in polar solvents. Ionic compounds have charges. Polar compounds have like a positive and negative side. So if you have an ionic compound, it's going to dissolve in a polar solvent. If it's a molecular compound and it's polar, it will more likely dissolve in a polar solvent. Polar dissolves polar. So like dissolves like. Ionic is kind of like polar. Polar is like polar. Non-polar dissolves in non-polar. So if it's all carbons and hydrogens, that's going to dissolve in all hydrogens and all carbons. And then the last very long paragraph is saying that if it has intermolecular forces like hydrogen bonding, it's going to dissolve better if the solvent has hydrogen bonding. So like dissolves like, ionic dissolves in polar, polar dissolves in polar, non-polar dissolves in non-polar, hydrogen bonding dissolves in hydrogen bonding. And we'll do one of these examples together. So then after we have this topic, and then we have one more we're going to go over to today, and then we'll cover the very last one next time. So this is something that chemists, they become familiar with. Oh yeah, this will dissolve my compound. Usually when you do a test on a molecule, you have to dissolve it before you can, there's some specific tests that you can check your compound. So to do those, you have to get them to dissolve. And so chemists go through this and they're going to think about what's going to dissolve my compound so that I can check it. And then usually, so if you have like just a tiny amount of salt sample, you want to make sure that you get the right solvent. But usually you have enough that you can test a few different solvents. So you usually have a good idea, and then you see, oh, it dissolved way better in hexane than polyene, something like that. Okay, so we're just going to run through these. I don't want you to memorize these. I just want you to see. You've seen before now. These are some common non-polar solvents. So hexane, we have a long chain of carbons and hydrogens. That's non-polar. This one in the center is called toluene. In my first week of grad school, I caught a beaker of this on fire. That was my first week of grad school. That was very exciting. Diethyl ether has a oxygen in the middle, and then it has a carbon chain on one side and a carbon chain on the other side. And then octanol is just a really, really long chain carbon, 8 carbons long, and then it has a OH group on one end. But we still consider it to be non-polar. There's mostly carbons and hydrogens. And then these are some really common polar solvents. So one on the left is called acetonitrile. We've already seen acetone. This middle one, N,N-dimethylformamide, is also called DMF. That's a pretty common one I've used. I think I've used all of these. And then the last one is DMSO. Sometimes that one, I've seen that one in so I've used that in the chemistry lab, but I've also seen it in a veterinary, I put something on my goat and it had DMSO in it. So it's a pretty common polar solvent. Okay, and then we're going to talk more about this when we talk about acids, but protic means that it can donate a proton. And so these are some of the common solvents that can give a proton. And this is really important for some chemistry reactions where you can get a proton, move a proton around, and you can get lots of chemistry to happen. These also have hydrogen bonding. So when we talked about if a compound has hydrogen bonding, it's going to dissolve better in something that has hydrogen bonding. These all have hydrogen bonding. So watch out for that. Okay, so let's go back to our Alex. Questions so far? Have you seen some of those solvents? Any of water? Hopefully you've seen water. Where's my mouse? Okay, and then, so we'll go over this one together, and then we have one more that we're going to talk about today. So we'll probably talk for 10 more minutes. Okay, this topic is called like dissolves like, if you want to follow along with us. So we get a solute, and then we have to pick between these two solvents. So remember things like dissolves like, polar dissolves polar, ionic dissolves in polar, and then hydrogen bonding dissolves in hydrogen bonding. So these look really similar, right? You agree with that? These look pretty similar. This one has hydrogen bonding. So notice we have nitrogen bonded to a hydrogen. This nitrogen only has 3 bonds, so it also has a lone pair. It's not shown. But there's also a lone pair on this oxygen. So this has hydrogen bonding, it's polar, and then let's go over here. This one has a nitrogen in the middle, and it has 3 carbon chains off of the nitrogen. So this one is not, this one is polar, but it doesn't have any hydrogen bonding. It doesn't have any oxygens. So out of these 2 solvents, I would probably pick this one because this is my reasoning. They look really similar. They both are polar, but this one doesn't have hydrogen bonding. If I had hydrogen bonding, that would be the better option, but this one doesn't, so I'm going to pick that one. Okay. So I got some wrong yesterday in my class, so I'm just trying to explain to you what I'm thinking, and then we can go back if I miss it. All right, this one, is this ionic or covalent? Or molecular, I guess. Ionic or molecular? This is ionic. So ionic dissolves in polar. This is ionic because calcium is a metal. So ionic dissolves in polar. Which of these is polar? You kind of have to know the structure. Corbin. Yes, CH3OH is going to be polar. We have the oxygen group. These look actually pretty similar. So we have the carbon with 3 hydrogens and an OH group. And then we also have carbon, and it has 4 chlorines. So remember, anytime you have 4 groups that are identical around a carbon, this is going to be non-polar. As soon as you get one different group, that's going to be polar. Okay, so ionic dissolves in polar. All right, next one. What do we notice about this molecule? We'll talk about these in chapter 11. So what do you notice about it? Is it polar? Does it have any hydrogen bonding? It does? Where? Okay, no, good. No hydrogen bonding, not polar. This is, we have 4 carbons plus, so this is hexane. We'll talk about that in a minute. So this one's going to be the best solvent because this is non-polar, this is polar. It's going to dissolve better in this. This is called carbon tetrachloride. Okay. All right. Let's check, make sure that I reason through that. Okay. This is a reasoning question. So just like think back to the reasoning question last, I can't remember what it was right now, but there was one in chapter 7. So make sure you're practicing that just like you did in chapter 7 so that when this shows up on the test, you're not like, oh, I don't know anything about this. Make sure you're really familiar. Yeah.
So the second outcome, the first one, that one's not polar, right? Even though there's
This one?
second outcome, the first.
This one.
Yeah.
Yeah, that would be. I think it's a little bit polar because what's happening is we have 3 carbons, 2 carbons. We have something like this. I'm just gonna draw. because there's only 3 groups bonded to nitrogen, so to fill its octet, it needs that lone pair. So it is going to be a little bit, like a tiny bit polar, but we have a lot of carbon and nitrogen, so not very polar. Okay, all right, do you want to do another one of these?
Yeah.
Okay. All right, this is called benzene. We have lots of carbons and hydrogens. This is non-polar. So which solvent do you think we should pick? So we have water and we have hexane.
The one that's not water.
The one that's not water, great. Lots of carbons and hydrogens will dissolve lots of carbons and hydrogens. Good. Okay, how about this one? This is a weird one. Is this ionic? No, this isn't ionic. This is covalent. Is this polar or non-polar?
No.
This is non-polar. So if it's non-polar, is it going to dissolve better in, so this one's non-polar or water? Non-polar. It's going to dissolve better in non-polar because it's non-polar. Non-polar dissolves non-polar. Okay, last one up here. So this one kind of looks like this one. What else do we see? Is there any hydrogen bonding? Oh, how about here? It can have hydrogen bonding. This one does. We have hydrogen bonded to oxygen, and we have lone pairs. There would be 2 lone pairs on this oxygen, 2 lone pairs on this oxygen, and we have hydrogen bonding over here, and we have a hydrogen bonded to an oxygen over here. So this has hydrogen bonding. I would say that it's polar. We don't just have carbons and hydrogens. So this looks pretty similar, but this doesn't have hydrogen bonding. So what I found yesterday when I was doing this with A-Day, we found that hydrogen bonding mattered more. So this one has hydrogen bonding. So if it has hydrogen bonding, you're going to pick the thing that has hydrogen bonding. Okay. So let's double check, but that's what we found yesterday. Okay. All right. So hydrogen bonding wins. Do you feel okay about this one? Do you want to do another one? One more? Okay, let's go. One more. Okay, how about this first one? This one's covalent. This is molecular. Which solvent are we going to pick? I think I heard somebody say something about it. You think the bottom one? Okay, explain your reasoning. Okay, we have the same thing going on. Does this have hydrogen bonding?
No. Yes.
Yes. We have nitrogen bonded to a hydrogen. We have lone pairs on the oxygen. So this has hydrogen bonding. Does this have hydrogen bonding?
Yes.
Yes. So both of these have hydrogen bonding, so that's going to be the better solvent. This is also kind of polar. This is hexane. This doesn't. Oh, maybe this one's not hexane. 3, 5. What's 3 plus? That's 5. This is pentane. So this one is going to be the better solvent. Okay, next one. What do you think? Water?
Yeah.
Okay. Why?
Because the thing that's being dissolved is whole liquid.
Okay, we've got all these OH groups. So. Yep, good. So hydrogen bonding. Yeah, and this one's kind of symmetrical, but there's enough unsymmetry that we can say it's polar. Okay. All right, last one for this topic. Good. Yep. So OH groups, that's going to be probably the clue. If it has OH groups, then OH groups. Okay. All right, let's check. Make sure. Okay. All right. Okay, one more topic, and then I'll let you have some more time. Oops. Okay, here we go. So The last thing we need to talk about is the solubility of liquids, or not liquids, solids and gases. So if we have a gas, do you guys know how to make it more soluble in a liquid? Or we have this table. We can. So if we have a gas, so think about pop. How do they get carbonation in the pop? What happens when you open pop? It fizzes. It makes a noise, right? So you're releasing pressure when you open pop. So to get the carbonation, to get that gas dissolved in the pop, they have to put a lot of pressure on the pop. So if you increase the pressure of a gas, or increase the pressure of the system, then gas will dissolve in the liquid. So increase the pressure will increase the solubility of the gas. Gas is opposite of solid. If you increase the temperature of a liquid, that decreases the solubility of the gas. It's opposite. So have you ever drinking hot pop? Like in the summer? So I don't know if you remember, but if you heat up liquid, then the carbonation will escape easier. So what's the opposite of that? How can we get more carbonation in our pop? Getting it to be colder, dropping the temperature. Yeah. So if we decrease the temperature, then gas will dissolve better. So this is why scientists are really worried about the oceans warming, because even if we increase the temperature of the ocean a little bit, gas will dissolve less in the ocean, and then fish can't get the oxygen that they need, even if the temperature decreases just a little bit. So, or increases a little bit. And then I think we're pretty familiar with solids. So if you want to make syrup and you want to dissolve a lot of sugar, how do you get it to dissolve? Increase the heat. So gases and solids are opposite. So if you're really familiar with like boiling sugar water, then just like flip that for gas. If I increase the temperature for gas, that's going to decrease the solubility. But for solid, if I increase the heat, that's going to increase the solubility. So this is another reasoning question in Alex. So if you understand these principles, if you get comfortable with those, then these reasoning questions will be okay. But they're still kind of confusing. So we're going to do a few together. Okay, I think, are we ready? All right, go back to Alex. This question is called Understanding How Solubility Varies with Temperature and Pressure, and it's just a reasoning question. Okay, so this says, a student sees tiny bubbles clinging to the inside of an unopened plastic bottle full of carbonated soft drink. The student squeezes the bottle. So what are you doing when you squeeze the bottle? What are you changing? The temperature or the pressure? You're increasing the pressure. Good. So what do we decide? If you increase the pressure, what happens to the solubility of the gas? It increases. Good. So we're going to make it more soluble by putting pressure. So what's going to happen? The bubbles will shrink and some may vanish. That's telling you that it's more soluble. So that's our correct answer. Okay. I have not seen this answer. They put this answer on as another choice. I need more information. I have not seen this one be chosen. So don't click that. Yes.
Okay, so if we decrease the temperature, it makes it less soluble. Or
Yes.
more soluble for gas.
Decrease the temperature, it makes it more soluble for gas. Okay. Yes. Okay, next question. A student has 2 unopened 33 centiliter cans containing carbonated water. So it's carbonated. I don't know why you would have carbonated water. Okay, can A has been stored in the garage at 32 degrees Celsius, and can B has been stored in the fridge at 8 degrees Celsius. So we're changing the temperature. The student opens one can at a time. Both cans make a fizz. So which one is going to fizz louder? So can A, which one's going to have more dissolve? The gas is going to be dissolved better. So what question are you answering? The answer or my question?
I was thinking it would be the answer.
Yes. Can A will have a louder fizz. Can you explain to us why?
Because so the way I was thinking of it was lower temperature makes the gas. Yeah, what he said.
It makes it stick in the liquid.
Yeah.
So can be at 8 degrees Celsius, the gas is going to be more dissolved. Yeah. At 32 degrees Celsius, the gas wants to come out. It's at a higher temperature. It's more likely to come out of the can, so it'll fizz more. It'll make a bigger noise. Good. Okay, thank you. Okay, these are confusing. Make sure you practice like a whole bunch of these, because this will be on the test. So if you can get really comfortable with answering these, that's one question that you'll have down. Okay, let's try one more. There's a gas one, and then there's also a, let's just skip this one. Let's go to, there's also a solubility one. Okay, let's do this one. It says 250 milliliter samples are drawn from a deep well bored into a sodium chloride deposit. Sample 1 is from the top of the well at 42 degrees Celsius. Sample 2 is from a temperature of 8 degrees Celsius. Both samples are allowed to come to room temperature. So note, this one is going down. This temperature will decrease. This temperature will be increasing. Okay, and it says blah, 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 blah. And sodium chloride precipitate is seen to form in sample 1. So we're taking sample 1, which has a whole bunch of sodium chloride in it. It's at a hotter temperature, so more sodium chloride will dissolve. And then we drop the temperature to room temperature, 20 degrees. And then because if we drop the temperature, it becomes less soluble. So if it's less soluble, they see a precipitate. Okay. All right, so let's look at the other sample. This sample starts at 8 degrees Celsius, and it increases to 20 degrees Celsius. So if we are increasing the temperature, is it going to be more or less soluble? More soluble. So are we going to see a precipitate in sample 2? No. We are not going to see a precipitate in sample 2. Because this one's increasing in temperature, so even though this one had a precipitate, because it's decreasing in temperature, that's why we're seeing the salt. Okay, questions on that one? So it's confusing. All right, last one, and then you can have the rest of the time. Rock candy is formed when excess sugar is dissolved in hot water, followed by crystallization. A student wants to make 2 bottles of rock candy. He finds an open box of cane sugar. He starts preparing by dissolving sugar in 500 milliliters of hot water, which is 70 degrees Celsius. He keeps adding sugar until no more sugar dissolves in the hot water. He cools down the solution to room temperature. He prepares batch B by dissolving sugar in 500 milliliters of water at room temperature, with no more sugar until no more sugar is dissolved. He lets the solution sit at room temperature. So then we have to answer this. Which batch do you think is going to form more rock candy? Yeah, carbon. Okay, batch A. So you both think that. Can you explain why? Why do you think A?
The solids melt under heat and then they solidify under cold.
Okay, so this one is at a hotter temperature, so more of the sugar will dissolve, and then they're coming to the same temperature. So this person could get more of the sugar to dissolve at 70 degrees. So when it comes to room temperature, they're going to get more precipitate. Good. So it's likely that more rock candy will be formed in batch A. Okay. So there's all sorts of variations for these questions. So don't just assume that if you get the well problem again, it's the same question. Make sure you read through it really carefully and think through it. Okay. All right. Questions for me before I let you work? We've got like 15 minutes. Okay. Very good.
I,